All right, so continuing on with our discussion of resistor applications, I believe we stopped here where we were talking about using resistors for biasing. All right, so the most common application for resistor is in current limiting. We cannot build any kind of electric circuit, electronic circuit without resistors, just not possible. Okay, so humble device, but very critical. And of course, because of current limiting and series connections, we can create voltage divider networks where we can take a voltage source, a single specific voltage source, create a resistive network divider, and we can obtain multiple voltage outputs from that circuit. So case in point was the previous Thevenin example where you have a 9-volt battery source and you wish to obtain a voltage other than 9 volts. Then we simply use a bunch of resistors connected in a series configuration, and we can obtain multiple voltage outputs. In this example, the output was a 5-volt source, meaning between terminals A and B, we would obtain 5 volts because of the voltage combination of 18 and 22.5K. Okay. Even though there are measurement terminals A and B, the two resistors are still in series. Okay. So from the perspective of the voltage source, the two resistors are in series. So let's say if we wish to obtain more outputs for any combination of 0 to 9 volts, 2, 3, 4, 5, 6, 7, 8, and 9. Then we can create a circuit like this with resistors that are all equal in value. And then connect our 9-volt source to those resistors. If they're all equal in value, then the 9-volt source will break up into 9 equal parts. So every resistor is going to have 1 volt across itself, measured directly across the resistors, okay? So 1 volt, 1 volt. And by combining any of these resistors together, 1, 2, 3, 4, 5, 6, 7, 8, 9. By combining any of these resistors together, you can obtain any combination of voltages between 1 and 9 volts. Does that make sense to everyone? All right. Here we are simply using 2 because you only need 5 volts from the output. Okay. This is in fact what happens inside your laptop adapters. Okay. A laptop requires multiple different voltages inside itself. One to power the CPU, another one for the graphics card, another voltage for the memory sticks. They all could be the same. They could all be different. USB ports are 5 volts. Digital logic circuits are typically 3.3 volts. So there's 2 voltage combinations right there. And the input that goes into your laptops would be at least 20 volts, if not more. So right at the front end, inside the laptop, you would have circuitry that will split up that 20-volt supply into multiple different voltages. Okay. And so we use resistors to create something like that. Does that make sense? Right. Again, this class is circuits and electronics. Typically, circuits and electronics are taken separately, but for CPE majors, we look at circuits from an application-based perspective. Okay, so we learn about resistors, we learn about resistive circuit analysis, but now we're learning a little bit about where we can apply these resistors. Okay, so this is one of the most common ways to use them. All right, and of course we spoke about the Thevenin resistance already. This was the same example as the previous one. Okay. All right. Other places where they are far common is in creating biasing circuits for electronic devices. Okay. So this is a transistor. This is something you'll study in EE 315. It's not until your spring quarter. Okay. So you're taking 115 now, 215 in winter, and 315 in the spring. Oh, by the way, I'm assuming that your department's already told you that this is the last year for 115, 215, and 315, right? CPE department has communicated that to you. So when you take 315 in the spring, that is the last time that it's going to be offered. Won't be offered again. After that, you need to take 3306 along with the other EE students. Okay. Because we're switching to semesters after that. All right. This is a symbol for a bipolar junction transistor, BJT, collector, base, and emitter. This is for informational purposes. This is not something that I will assess you on. Okay. We are not really concerned of this portion of the circuit. We don't really care what happens here. What we want to learn is this. Okay, the two resistors that are creating a voltage divider configuration. The information that I want to talk about here is in this kind of 3-terminal device, one of the terminals is common to the input and the output. In this case, it's the emitter, E. Okay, so it's common on the input side, and it's also common on the output side. So you have two Whoa. That's funny. I accidentally pressed. Okay. Well, it's time for me to get off the seat anyway. All right. So there are two terminals on the input side, two terminals on the output side. The device only has 3 terminals. Okay, so one terminal is common to the input and output. We are only concerned right now with the application of the resistors is on the input side. Okay, so on the input side, I need some biasing voltage. Okay, so voltage must be supplied on both sides, on the input as well as the output. So on the input side, I need a separate power supply. On the output side, I need a separate power supply. When I say separate, I'm saying different voltages. Okay. On the input side, the base side, the voltage is typically far smaller than on the output side. We are working as an amplifier, right? So amplifier is going to amplify a signal, but that energy does not come from thin air. That energy must be supplied. So DC voltages will supply that energy. So on the output side, that DC voltage is larger, 12 volts, 15 volts, 20 volts, and even larger than that. Okay. On the input side, we need voltages that are far smaller, typically less than like 5 volts or 3 volts, or typically less than 3 volts, let's say. So yeah, obviously on a lab bench, we can have multiple power supplies. We can supply it that way, right? We can have 2 power supplies if you're performing an experiment. However, if you're building an actual circuit for an application, like an actual amplifier device that you want to sell in the market, it's far easier to simply use a resistive circuit to provide those different voltages. And that's what the application is doing here. Still the same concept. It is still a series connection of resistors that is creating a voltage divider network. And the midpoint of the voltage divider network is creating a small voltage that is going into our amplifier circuit from the left-hand side. Okay. So those resistors are the 20K and the 3.6K. Okay. These two resistors right there. So 20 kilo ohm and 3.6 kilo ohm. And you're applying 12 volts between them. Okay, you're applying 12 volts between them. So if you look at the top of the image, the 12 volts is applied to the collector side, and it's also applied to the base side. So it's going into both. It's connected together. Okay. On the output side, it's just feeding into the transistor. On the input side, it's feeding into the transistor, but via the two resistors. And the midpoint right here is going into the base. Depending on the values shown in this example, we obtain 1.83. Okay, 1.83. Again, we are not concerned with what the circuit is or how it looks like, because again, as I said, that's not until you get to 315. But the application on the front, using the resistors, create a voltage divider network that allows us to supply a specific voltage to our device. Yes. So the value of the resistors. So the question being asked is, how do we obtain 1.83? The value of the resistors is 20K and 3.6K. And so the equation for the voltage divider network is you find Req, which is 3.6 plus 20. And in the numerator, you have 3.6 and then times 12 voltage division. Okay. So the base of the transistor is effectively receiving only 3.6 volts. The rest of it is dropping across the 20 kilo ohm resistor. We can say it's wasted energy, if you will, right? Because of the 20 kilo ohm resistor, current flowing through, and the rest of that voltage is not being used. But that's just part of the circuit. We can't build circuits without doing that. Yes. So the where on the, that's a good question. It's right there. This one. So it's here. Yes. It's going inside in the base terminal. Yep. Yep. Exactly. Yes. That is correct. I had never thought of that, but yes. Yeah, we could put an LED in there, it would turn on. But then the LED would sink a lot of the current, so then the transistor may not work. Transistors are complex devices and require specific biasing to operate within. So we spoke about biasing a little bit, I believe, right? We constrain our system, we constrain our device to work according to our application, right? So transistor biasing is the most important thing we can that is required for the transistor to operate. And that biasing requires complicated equations. So the resistor values and the voltage values that we're supplying here have a lot of analysis behind them. Okay, and again, it's not something that we look at in 15. Okay, so yeah, that's the voltage that's going into the transistor. And again, the application is simply the same. We have a biasing network created from two series connected resistors. And then the Thevenin voltage, sorry, the Thevenin resistance can be determined by simply this. So this is your circuit, and the Thevenin resistance would put 20K in parallel with 3.6K. Remember, to find Thevenin resistance, we reduce all sources to 0. So if your voltage source, 12-volt source, is reduced to 0, it's replaced with a short circuit, meaning that point at the top of the circuit is now connected directly to ground. So that puts both resistors in parallel, and that's why we obtain 3 kilo ohms. Okay. Other places where we apply them is in same kind of voltage reduction or voltage division principle, and it's applied to a circuit known as an op-amp. An op-amp is something we study here in this class. Okay. An op-amp is short for operational amplifier. Operational amplifiers are something that E students will study in depth in 307, 308, and 409. But we are not worried about the internal circuitry of the op-amp. What we are looking at an op-amp is as a building block, as an off-the-shelf component, and we build a variety of circuits using this component. So it's a very important component in electrical engineering. Again, op-amp stands for operational amplifier, right here. And we can create a variety of circuits using this component. And more commonly, we use it to implement a variety of mathematical operations. So addition, subtraction, differentiation, integration, filtering circuits, voltage follower circuits, unity gain buffer amplifiers. All sorts of circuits can be created using an op-amp chip. All right. So we will study op-amp in 115 as a building block for larger circuits. But one of the things we do is we can bias. We can again bias the circuit using resistors. And here the resistors are labeled as R2 and RF. We'll see later that F stands for feedback from the output to the input. But the voltage V1 is a voltage that is derived from the series connected network of R2 and RF. Same equation. So a portion of the output is fed back into the input. Hence the name RF. Okay. A portion of the output is fed back into the input. But again, same application of resistors. Two resistors created a voltage divider network, and a portion of the output is fed back into the input. One other place where you have seen this is when you use oscilloscopes. If you use a regular probe like a BNC connector and you just plug it into the oscilloscope, that does not have any reduction circuitry. But if you use the actual oscilloscope probe, the terminal is slightly engorged right at the front panel, and you can see those right behind you, front panel. So inside that probe at the, sorry, not at the probe tip, but at the end where it connects into the oscilloscope, there is a circuitry. The circuitry consists of resistors and capacitors. And again, as it stays here, we are not worried about capacitors. That's part of 215. But the resistor is creating a voltage divider network in a ratio of 1:10. And so technically, these oscilloscope probes, let's say the oscilloscope can measure up to 20 volts. But if you connect a 10:1 probe at the front end, then you can measure up to 200 volts. Okay. Because any voltage you apply at the probe tip is going to step down to up to 10%. Hence the name 1:10 probe or 10x probe. In the lab, when you're doing a measurement like this, you need to ensure that the manual switch is set to the same settings that you plug into the oscilloscope. The oscilloscope needs to know what setting you are using at the probe. Okay. And so that's another application of resistors. All right, we'll end class here today. We'll pick up here again on Wednesday. Things are going to get more interesting from here on out. Okay, gonna look at applications and lots of new stuff.
Getting here like very late, 2 minutes so we're on the quiz and got absolutely nowhere. And wondering if there's any chance I could take it in August or is,
You want to take it now?
I can take it now.
Let me set it up.